Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today I'm delighted to have Eric Chung with us. Eric is a PhD student advised by Professor James Ho at the Electrical and Computer Engineering Department at CMU. And today he will talk to us about accelerating full system multiprocessor simulations using FPGAs.
Thanks, Angan. So it's a pleasure to be here today to talk to you about some of the work that we've been doing at CMU on how we can use alternative technologies such as FPGAs in order to accelerate the performance of software-based simulation. This is work done with fellow graduate student Eriko Nervatati, my advisor James Ho, and professors Bobby Filsafi and Cam Mai. And this work is under the umbrella of the ProtoFlex project at the Computer Architecture Lab at CMU. So I want to begin today by first just telling you about the current state of full system architectural simulation. So full system simulators are software tools that are widely used in both the hardware and software community. These tools are important because they can essentially work as an effective substitute for hardware systems that normally might be hard to get, or hardware systems that don't even exist yet. And some of the key features of these software tools is that they can model systems to a level of fidelity such that you can run and boot your unmodified commercial operating systems. You can also run applications that which you might not have the source code to. And just to be clear throughout this talk, when I refer to full system architectural simulation, I mean simulation as in like instruction set interpretation. So nothing that, not cycle accurate simulation. And so these kind of tools are important in software research, for instance, to provide a level of abstraction for the programmer. So for instance, if they want to do deterministic multi-threaded debugging, or to try out new architectural ideas. They're also widely used in computer architecture for a whole lot of reasons, some of which include something like you might be doing cache-based simulation, or you might use these tools to warm up microarchitectural structures prior to cycle-accurate simulation. And so sort of a very well-known tool that's used in these areas is a tool called Virtutech Simics, and there are a couple others. But here, that sort of captures the essence of it, where you can model $1 million server machine on a PC workstation. While these tools have been working well for us for the last 5 to 10 years, we sort of are running into a problem now where when we want to simulate systems with ever larger configurations, the simulation turnaround time becomes a major bottleneck. And the main problem is that most of these simulators, which have been developed for a very long time, weren't written with multicore in mind, and so they're just going to stay at a level of performance that of yesterday. And this presents a really serious challenge when you start talking about, well, you want to architecturally simulate and study systems incorporating up to hundreds or even thousands of processors. And to give you a concrete example of this, it already takes us 2 hours to functionally simulate just 1 second of a 64 CPU system. And so our work looks at alternative technologies such as FPGA emulation in order to overcome some of these simulation bottleneck challenges. Some of the key advantages of FPGAs are, in case you're not familiar with them, is that they're essentially like real chips, but they're completely reconfigurable. So you can reconfigure them as many times as you want, and they only run about 10 times slower in clock frequency than real hardware. But before we get too excited and jump on this FPGA bandwagon, we need to think about a couple of issues. First is when we make the transition from flexible, visible, software-based simulation into hard to observe hardware emulation using FPGAs, we're also introducing this hidden complexity here. So there are two main issues. One is if you're talking about emulating very large-scale configurations using FPGAs, you can imagine trying to put together a 100-way or even a 10-way system on an FPGA, so connecting a bunch of FPGA soft cores together, that introduces a level of complexity that wasn't seen before when you were writing your software simulator, right? Software simulator, you just instantiate. And so this is a very serious problem if you want to look at 1,000-way configurations. The second problem has to do with the fidelity of the simulator. So most full system simulators today, as I said, they can run and boot unmodified operating systems, and to do that, you need all this cruft on the side, on the right. Right? It's not just processors and memories that you're talking about. There's I/O interaction, system calls, things that a user level stuff that's well beyond the comfort zone of implementing a user level simulator or user level emulator on the FPGA. And so I'm going to argue that simply taking a naive build-all strategy in the FPGAs, it's not tractable. It's going to significantly elevate the barrier of entry of this technology. It's cost you a lot of human resources and effort, and so this isn't the way to go. So rather, our work applies the well-known idea of virtualization in order to overcome some of these implementation challenges using FPGAs. And we sort of adopt two very broad definitions of virtualization. On the left, the first definition is making a single physical resource appear as multiple logical resources. And this is sort of a well-known idea, and we call it virtualized multiprocessor emulation. And what I'm showing you here is that what's shown in the green are processor models that are in your target system. So you had in mind you want to model the behavior of 5 processors, but in fact, on the FPGA, you only have a single processor, and you're multiplexing the logical architectural execution of these processors on a single resource. And the key here is that we're decoupling. We're decoupling the logical target configuration from that of what's implemented in the underlying host. The second idea of virtualization is sort of the opposite. One is which you make multiple physical resources appear as a single logical resource. And this technique is mainly done to address the complexity of full system. And so if you look at what's in this green box over here, which I show target full system behaviors, you can think of that as the complete set of behaviors that occur in a full system simulation. And you can categorize those behaviors into those that occur very frequently and those that are infrequent. And what I'm showing you in the blue are hosting resources. I have an FPGA which is there solely to accelerate the common case. And so this is kind of like manifesting Amdahl's law, where you want to make the common case very fast, but then you want a complete system and it's correct, right? So all infrequent behaviors can be relegated to software simulation. So we want to look at a combined approach. And the key benefit here is that it turns out that a lot of the infrequent behaviors also turn out to be the most complex ones. And so there's a lot of gain here. So this is the outline of my talk. I'm going to first talk about hybrid full system emulation. Then I'll talk about virtualized multiprocessor emulation. I'll talk about an implementation and prototype that we've done. I'll present an initial evaluation, and then I'll conclude. So hybrid full system emulation. So what I'm showing you in here in this picture, within the box is sort of a textbook example of a complete system, right? You have many processors, you have memory, and you have devices. And this is what we normally do with our full system simulators. We simulate all of these behaviors in software on a PC workstation. And keep in mind, these devices are not the devices of the PC. It's simulated. And what we're going to do is we're actually going to split this target model into 2 different hosts. So on the left side, we've introduced the FPGA host, and on the right side, we still have our existing software-based full system simulator running on a PC. And there are 3 ways in which we can take these target components, these boxes I've shown, and map them onto these different hosts. So of course, you have components that are emulation only. So for instance, physical memory. So we map the physical memory of the target machine onto the FPGA, and it remains there indefinitely. The second class of components are those that remain in simulation indefinitely, so things like devices. And the reason why you can do this is that device interaction actually is relatively rare compared to advancing the instruction stream. And the last component is called transplantable. And transplantable components pertain specifically to processor models. So what I've shown you in the blue. And they have the ability to be reassigned during dynamic runtime between hardware and software. So the way this works is that imagine that that on the FPGA host I have a processor model, but it's not complete. So I might not implement all the instructions, and if I hit an instruction or some I/O behavior that I don't know how to implement, I'm going to transplant it over from hardware into software. And I'll tell you a little bit more about the details later how that works, but the purpose of this is so that, so in this example, we transplanted the processor, and it might, for instance, be able to execute an I/O instruction that wasn't implemented on the FPGA. And then once we're done, we can resume execution in hardware. And so the key thing here is that by having software as this backing substrate, we don't have to implement everything. And in fact, we only have to implement the common case instructions and behaviors on the FPGAs. And then we can relegate things to software using the transplant method. And so I'll give you an example in the next slide. So going down as time, where on the left side I have what I call the partially implemented functional processor in the FPGA. So you can think of this as just the bare minimum of the instruction set architecture, the bare minimum of instruction set architecture. And as I'm executing loads and adds, I run into an instruction like an I/O store, which I have no idea how to handle because I don't model the devices on the FPGA. And then I'm going to carry out a transplant into software. Once I'm in software, I have a complete system, and I go ahead and execute the I/O store. And then once I'm done with that, I'm going to take any updated state of that processor and bring it back to the FPGA. And then I'm going to resume executing. And there are other behaviors that you could potentially relegate as well, like TLB misses or whatnot. So again, before we get also too excited about this idea, now aren't we actually making the uncommon case very, very slow? Because after all, we're sort of marshalling data off of an FPGA over who knows what and bringing it to a PC and then bringing it back. And in fact, that is the case. And so it's worth thinking about it's worth doing sort of a thought experiment, or a sanity check. So in our implementation, actually, transplants are very expensive, on the order of a millisecond. And so we do some quick calculations. If I had a soft core on an FPGA running at a CPI of 1, so it can retire one instruction per cycle, and running at 100 megahertz, so I have 100 MIPS. If I were to just carry out this transplant operation between hardware and software, at most once per 100,000 instructions, this effectively reduces my performance by half. So I'm giving a lot of performance and not gaining much because, I think a lot of things do happen a lot of things that are complicated do happen more often than 100,000 instructions. It may seem that this isn't going to buy us very much. So what we do is actually we sort of think back to how caches work, where a single monolithic cache may not get you the best overall performance, so you can do a multi-level. So what we observe is that on modern FPGAs, they don't just give you a bunch of gates. They often include system-on-chip solutions. So an example is like Xilinx. Xilinx FPGAs actually include an embedded hardcore that runs at a couple hundred megahertz within the reconfigurable fabric. And so you have very low latency communication. And so we thought, well, why not actually take advantage of this nearby embedded processor and actually have it carry out some of the behaviors for us. And so we call these micro transplants, where you sort of run this ISA simulator kernel on a nearby embedded core, and it actually doesn't have to be a hard core. You can actually, if you don't have a hard core available like in Altera, you can drop in a soft core, and essentially what's running on that core is just typical like C code, for instance. It's just simulation code. And of course, there's a communication fabric between our own implementation and this nearby core, and it's going to be about 1,000 CPI in this example, but it's still a whole lot better than incurring a millisecond. In fact, the only time we ever have to go to a full system simulator is when we have I/O interaction. So all instructions are actually carried on chip on the FPGA. So these two in combination will carry out all the instructions. Down here we do I/O. And here's a more concrete picture of what's going on. So on the FPGA, I have a partial CPU model on the left. It can communicate to a simulator ISA kernel on the order of microseconds. And this gets me almost 100% instruction coverage. And over here, the full system simulator is entirely there to model the I/O behavior, so I/O devices. So when you look at this picture as a whole, we haven't given up anything in the fidelity of the model. So we can still run a full operating system. We can still run commercial applications, and it has no idea that any of this is going on. So this is below the level of abstraction of the architecture, the ISA. And this is just another example that extends from the earlier one, where now I/O stores go a millisecond, and then now you have microseconds for something like a data TLB miss, which is just a local state update. So now that I've talked about hybrid full system emulation, I'll now discuss virtualized multiprocessor emulation. So I want to sort of start this portion of my talk by asking, how do you build a 1,000 CPU FPGA, functional architectural simulator? And the answer isn't obvious, but I'm going to answer this question by asking another question, which is, well, how fast should functional simulators have to be? And so the hypothesis is that future studies will want to evaluate systems with up to hundreds or even thousands of processors. And by today's standards, I think people have generally found it that a 10 to 100x slowdown in simulation performance has been acceptable for interactive use. So a concrete example is like Symix, where it's still fast enough that you can actually, you can still compile code in the target machine and run it. For computer architecture research, a 1,000x to 10,000x has probably been pretty good for functional design exploration. So if you're doing cache-based simulations and you batch them all, then everything's good. And so what I'm showing you on this graph here, there are two axes. On the y-axis, I'm showing you the slowdown of a given simulator relative to the real system. And along the x-axis, I'm showing you the size of the simulated system that you're trying to model. And the green and the red bars show a 10 MIPS simulator and a 100 MIPS simulator respectively. And you can kind of see that, and I'm also assuming that a real CPU runs at 1 GIPS in this example. But you can sort of see that in between the green and the red is sort of where we are today. And yeah, question?
So when you refer to architectural functional design space exploration, I do understand that, for example, if you're doing just functional cache simulation, then this is pretty much all you have to do, in the sense that you have to just basically emulate the code. Well, at least just emulate the ISA and not the machine in a lot of detail. But for many of the other kinds of studies that you might be interested in doing, you would need actually a detailed model of the CPU.
Yes, so that's a very good question. I think our work is mainly focusing on sort of non-core research. So if, for instance, if you're interested in coarse-grained performance estimation, so you want to study, the topology of an interconnect, or you want to look at, how a cache subsystem might work, and you want some coarse-grained performance, what you can do is actually take our infrastructure and attach instrumentation to it.
Right. And I guess my question is,
so this is not cycle accurate simulation.
Right.
You're correct.
That part I
yeah,
completely
right.
understand. The only thing that I'm wondering is, as I keep adding more and more of this functionality to the simulation infrastructure, so that I can take into account more detailed models of some of these other subsystems that are existent. So, for example, I might attach a cache subsystem to this, and then I might attach a DRAM subsystem to that, and all of those will also, of course, factor into the final simulation time. Do you think that the final amount of time that's spent in functional simulation will be a significant portion of the overall simulation time as I keep adding these other components?
I think it also, okay, that's a very good question, and it has to do with what's sitting on the other end if it's going to slow down the functional simulation. That's your question, sir. Right?
As in most situations in which you may want to use this infrastructure, do you think that this would actually be the main bottleneck, which would?
I think it depends. I think if you're doing a sort of a functional cost model on the other end, where you don't actually need 10 cycles to say that this event costed 10 cycles, then you probably don't have a bottleneck. For things like you can do, for instance, what we've been able to do is model the functional behavior of a CMP cache on the FPGA. And so what we can do is actually consume traces and actually model all the coherence activity, but we don't actually slow down the functional part either, because the receiving end actually runs in parallel as well. So I think it can be the case that if you don't implement the receiving side as fast, then that portion will become the bottleneck. Yeah. So what I'm going to show you now here is what a hypothetical 1,000 MIPS simulator might look like. And I'm going to argue that tools are needed sort of in this domain, where we need about a 10 to 100x speed up over our current tool, so at least a GIPS in this particular example. And so of course we're interested in using FPGAs in order to achieve that kind of performance. And so going back to the question is, how do you build a 1,000 CPU FPGA based emulator? And so let's run through a thought experiment. So we want to architecturally run 1,000 processors. And let's say our pain threshold was that we wanted to be within 1,000x slowdown relative to the real system. So what that means is that a single processor that has to advance at a rate of 1 MIPS. So what that means is that my overall desired emulation throughput must run at 1,000 processors times 1 MIPS, and that's going to total up to 1 GIPS. And so if we simply took the build-all approach, like I mentioned earlier, and just dropped down 1,000 FPGA soft cores, and each of these maybe are running up to 100 MIPS, of course I'm going to meet my target implementation requirement, which is I want to model 1,000 processors. I want to run at least 1 GIPS, and I'm getting a whole lot more performance, and I'm not going to complain about it, but to actually do this is sort of encroaching on what it would actually take to build a very large-scale multiprocessor system. And so the virtualized approach tries to decouple this. So imagine that we start with just 10 FPGA cores. Each of them can sustain a throughput of 100 MIPS. So now my overall throughput is 1 GIPS, and I'll simply just multiplex 100 logical processors onto each of these cores. And so I've sort of met my minimum requirement, and I haven't done any more work than I needed to. And so just to summarize what this is, the problem is that large-scale configurations are hard to implement in FPGAs. So the solution here is to decouple the number of logical processors that we're implementing in the target model from that of the physical. And the advantages here is that ideally you could have flexible emulation configurations independent of the size, and your implementation only reflects how fast you need the system to be. So if you want a faster, higher throughput emulator, you simply drop more of what I've shown in here, these host CPUs, in which I'm multiplexing a bunch of logical cores onto. So now onto the details. So what's inside one of these FPGA host CPUs? It's really just an engine that can architecturally execute multiple contexts. And so it turns out that in the literature there are a lot of multi-threaded designs that are very good candidates for this type of thing. And we think the choice is not going to be fixed, and it's really influenced by what kind of level of decoupling. So if the ratio of, whether your ratio of logical CPUs to physical CPUs is high or not. And so for our purposes, we propose implementing an interleaved pipeline, instruction interleaved pipeline. So it's kind of like a Terra-style processor, and this is very suitable for a high logical to physical CPU ratio. So the basic idea is that you would switch in a new processor context on each cycle, and it actually is a very simple, efficient design, even simpler than an in-order 5-stage pipeline. There's no stalling or forwarding, and you also get long latency tolerance. So if a thread is off doing cache miss, other threads can come in and fill in for it. And this can actually aid with the transplant overheads as well. And also, if you're implementing caches within this host CPU, in some sense you get coherence for free between logical processor contexts that are mapped onto this host CPU. So now that I've talked about the conceptual ideas, I want to go into an actual implementation that we've been working on over this last year called the BlueSpark, and incorporating these two ideas I just presented. So we call it the BlueSpark simulator, and it models the functional behavior of a 16 CPU UltraSPARC III server. And the platform we're using is the Berkeley Emulation Engine 2. It's an FPGA board with 5 FPGAs, and we're also using Simics to model the devices for us. And so on the FPGA, you can see in this box here, we implement a 16 CPU context interleave pipeline. So it's just a single pipeline. We replicate 16 processor contexts. Again, as I mentioned, we use the PowerPC, which is the embedded hardcore on the Xilinx chip, in combination with Simics to model everything else that's not implemented in here. And we also implement the DDR controllers on chip. Just to be clear, so there are 5 FPGAs, but we're only using 2 of them right now. So one FPGA, the center one over there, hosts the pipeline, and then another FPGA actually hosts all the memory controllers. And I'll explain later why we do that. So these are just more detailed information about the BlueSpark simulator. It's actually a 14-stage instruction interleave pipeline, and I'll talk on the next slide why it's 14 stages right now. We implement level 1 caches just to reduce bandwidth to the main memory, and it is a non-blocking memory subsystem that we implement. Currently we're running about 50 megahertz, although we have been able to place and route the design at 80 megahertz without any effort. The main reason why we haven't been able to measure it at that performance is we've had some unresolved clock synthesis issues, but that's being taken care of at the moment. And these are just some stats about the latency of microtransplants and transplants, so different orders of magnitude. We have a 4 gigabyte main memory subsystem. And in terms of resources, without any monitors or stats, we're roughly about 50% of a very old Xilinx part. And I think down here, the block RAM consumption is actually very high, so about 70%. And block RAMs, if you're not familiar with, are just basically SRAMs that are on the FPGA available for general purpose use. And the reason why the state is so high is because for UltraSPARC III, the TLBs are actually architecturally defined. And so they architecturally define, a 512 set data TLB, and you have to replicate 16 of those. So that actually dominates the amount of storage that we need on chip, and it's in fact limiting us in the number of contexts that we can drop down. So some future work will look at how we can maybe potentially page state in now, or just keep a cache of the state that we need on chip. And I think one key feature here is that the simulator is entirely instrumentable on the FPGA. So as I mentioned earlier, we've been able to do things like cache simulation, and so you can probe into any of the state, and for instance, like memory references, you can collect those, or if you want to do branch predictor studies. I think the key contrast here is that you can do this instrumentation without without necessarily slowing down the implementation of the functional simulator, because in software, for instance, once I enable probing, I tend to lose maybe an order of magnitude or 2 of performance. And one thing I do want to point out is that we don't use a conventional hardware description language for this implementation. We use a new HDL called BlueSpec System Verilog. And the interesting thing about BlueSpec is that it's a very high-level harder description languages. So you have very strong types. It's a strongly typed language, and it's got a couple nice features that preserve high-level programming abstraction. And so I won't go into details about that, but if you actually just peek into, for instance, some component in our design, like the decoder, it reads a lot like a simulator. And so the whole point of this is that we can have a model that's high-level enough, it's malleable, but it also synthesizes to hardware. So this is a more detailed view of what our microarchitecture is. So I'm showing you the 14 stages. The numbers at the top show you where each cycle is. And so what's shown in the blue are sort of the conventional stages in the pipeline. You notice the ALUs are split into two because we do a 64-bit architecture, and it was just necessary to keep the timing okay. And what's shown in the orange are the states, the places where we had to replicate the states. And so you can see the TLBs, they constitute a lot, the register file, the PC registers, the processor state registers. And one thing to notice is that we're spending quite a number of cycles in the TLB lookups. And the main problem there is that because there's actually two TLBs for the instruction memory and the data memory. So, and the problem there is that these TLB configurations are architecturally defined. So they're software visible. You can actually issue loads and stores into these TLBs, and things had better, you can't actually change that. And so that turned out to be there are actually special SPARC loads and stores that can actually load out of a specific entry of the TLB.
Oh, really? So like load
TLB.
13, TLB entry number 13.
Exactly. So it turned out we thought SPARC would be a very nice, easy ISA. Then you look at all the privilege level stuff, then you look at all the implementation dependent stuff, then you notice that the UltraSPARC III ISA manual is about 5 times as thick as the normal SPARC one. And there's a whole bunch of ASI modes that I haven't even talked about, but so those things kind of made our implementation on this side a little painful. And you notice that the data TLB is actually 3 pipeline stages, and the problem there is that there's a fully associative structure, 16-way, that had to be there, and we couldn't fake it with a direct map structure because from early profiling, as it turned out, for some commercial applications, you do use all of the entries in that fully associative structure. So we had to put it there to keep the performance good. Last but not least is all the transplant, the hybrid simulation stuff. And so these are all the components that are used to carry out those operations. So the transplant unit takes inputs from the decoder. So if the decoder notices some unimplemented instruction, we'll pass the instruction and word along with the processor context ID. And also, we also get transplant requests after the data TLB stage. And that's because in SPARC, the memory mapped I/O isn't determined until after translation. So you don't know if the load or store is memory mapped I/O until then. So then this thing actually interfaces over a bus to the internal power PC, which is the service processor, which in turn can also issue accesses to what I call the assist unit here. And the assist unit can actually issue helper instructions through the pipeline. So if you need to pick up any state or update any state, you can do it through that. The assist unit is also there to handle some of the more complicated instructions that require multiple passes. So an example might be a 64-byte load into 8 registers. That requires like 8 passes. So this is how we actually partition everything across this hardware and software substrate. So we do implement a lot of stuff in hardware on the blue SPARC on the left there. We do the register windowing stuff with SPARC. We handle the interprocessor cross-calls, which, believe it or not, actually happen in some commercial applications. We handle all the TLB misses ourselves because, at least in Oracle, TLB misses are on the order of hundreds of, once per hundreds of instructions. We do all the atomics. And over here on the Power PC, these are some categories of instructions that we were able to omit. So for instance, most of our workloads, at least, may not be yours, but most of our workloads made very little use of the floating point unit. So in fact, we were able to completely omit the floating point unit and just do it in software. Now keep in mind, even though we're doing it in software, that doesn't mean that the simulated target machine actually knows that. Right? We're not actually trapping on a missing floating point unit. It actually thinks it still has it. It's just running really slowly. And there's a whole bunch of diagnostic stuff, ASIs that are SPARC related that we don't do. So this list sort of doesn't do all this justice, but there is a lot of stuff, a lot of cruft that we were able to leave out of the implementation. And down here in off-chip simulation, so in Simics, all these devices we didn't have to touch. We didn't have to implement any of them, and they're already been validated for us. So now I'm going to talk about some early evaluation that we've done with our platform. And so what we did is we compared BlueSpark to what would be the predicted ideal performance. And this is entirely done through event counters that we've added into our implementation. However, it's ideal because it doesn't account for things like serialization. So if I have back-to-back memory misses in the memory system and there's some queuing delay, I'm not accounting for those in the ideal performance. Simics Fast is just taking Simics straight out of the box, run it on the fastest Core 2 Duo you can find, and then measure its performance on the workload. Simics Trace is probably a more interesting, is probably a more common use case where you do enable the instrumentation. So in this case, we're probing on every fetch and memory reference. And we studied 3 benchmarks. These are 16 CPU benchmarks. The first is there are 2 multi-program spec-int benchmarks, so Crafty and GCC. And we also run a tuned database workload. So this is OLTP running the TPCC transaction processing benchmark using the Oracle 10G database manager. And all of these benchmarks are unmodified, and we can actually run this in Solaris 8. And also, these workloads existed prior to this infrastructure ever coming up. So these workloads are actually saved in a Simics checkpoint format, and we can actually load unmodified Simics checkpoints into our infrastructure. So if you have workloads that you've developed over the years, you can use our infrastructure. And so this is the performance. And so on the y-axis is just raw MIPS, and on the x-axis are different workloads. And on the far left bar, you can see that the BlueSpark ideal predicted is higher than the actual, so comparing the gray to the blue. And one thing you'll notice also is just that Oracle is doing a whole lot worse than everybody else. And that's true for our emulation platform and also true for Simics. So Oracle is just a very, very tough application. One thing you'll notice, so as I mentioned, the ideal and the actual performance, which is that actual performance of BlueSpark running at 50 megahertz, there's a difference. And that difference is coming from serialization that we're not accounting for. And so if you have serialization on the I/O or the transplant unit or the memory subsystem, the ideal performance isn't estimating that yet. But once we put in more counters, the ideal should get closer the predicted ideal should get closer to the actual. Now, one thing to notice is that comparing our implementation to Simics in black box mode, we're comparable in performance right now. So running just about as fast as Simics can. But this is, again, as I said, we're sort of running at a clock frequency that's lower than what we actually can. There are also other factors, which is the memory subsystem performance, but I'll talk about that in the next slide. One thing to notice is just that once you enable the instrumentation on Simics, you compare Simics Fast to Simics Trace, you lose almost an order of magnitude of performance. And so that's sort of where we're trying to get at, which is hopefully we can actually run at full speed and be able to instrument but not have to suffer the software slowdown, the sequential slowdown that Simics does when you turn on the instrumentation. And so on average, we're getting about 22x speedup over the Simics trace, and we're also comparable to Simics fast. And this shouldn't be thought of as sort of the final result. I mean, this is just, our implementation is definitely not optimized. We're sort of just aiming for correctness at the moment. So we're not trying to build the fastest thing that we can right now. And so there are some first order effects on ideal performance. So why is Oracle doing so badly in our implementation? Since it turns out Oracle experiences a high rate of serializing cache flushes. And these happen in our implementation when there's any possibility of I or D cache coherence. Now, for some of you who might know a little bit about SPARC, SPARC actually architecturally defines a flush instruction which allows you to implement incoherent I and D caches. When we looked up the UltraSPARC III manual, the flush instruction is a no-op. And in fact, the UltraSPARC III implements coherent I and D caches, and we don't. And as a result of that, Oracle, which for whatever reason has some kind of self-modifying code, at least possibly in the operating system, causes us to lose a large fraction of our performance. And so we're hoping to fix this problem by simply adding I and D coherence in our implementation. In general, across all the workloads, you have a high rate of cache misses. And so roughly 1 in 10 instructions. So that's not a 10% rate of the cache number, total number of cache references per instruction. And so in combination with the fact that our memory miss latency is very high, so it's already 30 cycles actually at 50 megahertz. And as I mentioned earlier, we actually moved the memory controllers to another FPGA. The reason why we did that is it's not fundamental at all. It has to do with the B2 platform that we're using. The B2 DDR2 controllers only support up to 1 gigabyte of memory. So in fact, if we had one controller that could index up to 2 gig or 4 gig, then we wouldn't have this problem. And in fact, the single controller can sit on the same chip as our pipeline. But we need 4 gigs of memory, so we need 4 controllers. The implementation of the DDR controllers that was handed to us from Berkeley, they're big resource hogs, so we weren't able to meet timing if we try to drop down all 4 DDR controllers with our design. But future implementations, I think it's not fundamental to these ideas. And so there are also a number of things that we can do to try to lower the latency. So for instance, we're not doing target word first fills to the cache. And so because we have these links between the FPGAs, which are pretty narrow, we're fragmenting a 64-byte block across, and we're waiting for all of that to be finished before we return it to the processor. So these are just things that we did for now to make it correct. I already mentioned why the ideal performance doesn't match the actual. So what are some of the future plans? Well, of course, we want to improve the single engine performance, and we expect to comfortably reach 90 to 100 megahertz. We've already gotten it to 80 megahertz. As I said, improving the IPC of this engine, we want to lower the memory latency, get rid of the flushes, and potentially also maybe even go superscalar. So we can share a cache port on a two-wide pipeline, interleave pipeline, potentially get a little bit more throughput. What we also want to do is get more context on this thing. So 16 is kind of our limit right now. That's the sweet spot. And as I said, it's for the data TLB. So we're actually looking at ways in which maybe we can page some of the state in and out of memory. For example, SPARC register windows. You have 8 windows, but you're only using 1 at a time. So you, in fact, don't need all 160 registers sitting on chip. And of course, we want to. This isn't the end of everything. We want to be able to scale up the number of engines and get more throughput out of this implementation. And so we're only looking at maybe up to tens of engines to meet our performance goals to get up to 10 to 100x faster than our simulation infrastructure. So we think that a very simple interconnect fabric between engines will be sufficient, something like a Snoop-based coherence protocol. One thing that was completely shoved underneath the rug, which we actually didn't think about till after everything was all done, was like, well, how do you actually emulate enough memory for 1,000 way multiprocessor system, and that's something that's not necessarily easy to cheat with, like what we've been doing. So we're actually looking at hardware-based memory virtualization techniques. So you can imagine, now physical memory on the FPGA is really just a cache of a larger backing disk storage, perhaps. So maybe you implement some kind of hardware demand paging mechanism. Last but not least, of course, in our laboratory, we rely heavily upon sampling-based simulation technologies in order to do cycle-accurate measurements. And we think that our infrastructure can actually accelerate this process even though we don't do cycle-accurate simulation. And the reason why is in sampling-based performance studies, it turns out that the turnaround time bottleneck is ultimately determined by how long it takes for you to fast forward through a program and run a functional cache simulator to warm up the state right before you take that measurement. So that process actually for us takes on the order of days to complete, sometimes up to a week, just to be able to generate the measurement points. And then when we actually run the very detailed, slow cycle-accurate simulators, that's just a matter of hours. And so we're hoping that this infrastructure can actually bring it down to within hours to do the functional cache warming. And so before I conclude, I want to give you a short demo of our thing working in action. Again, as I said, it's running on the B2, and demo application is an online transaction processing benchmark, so TPCC and Oracle. I already told you all that. And you can see here, this is where our BlueSpark implementation is, the interleave pipeline, the memory controllers, and this is the Ethernet going to Simics. And this is for debugging. Okay. So this is actually a recorded demo because I wasn't sure if I could get wireless here. Okay. So this is actually a remote server that controls a power switch which turns on the B2. And this is a hyperterminal connected over RS-232 to the B2. You can see that it pops up with a console. But in this black screen, I'm actually running a command that downloads a bit stream, a pre-generated bit stream onto the B2. And so we're going to go through all the motions. There might be a part later where I fast forward it, but what this process is, we actually have to download 2 bit streams on the B2. So one is the central FPGA that hosts the BlueSpark pipeline, and then there's the peripheral FPGA with the memory controller. So one goes first, and then it itself will program the other one. And so if this takes too long, I can just quickly. Yeah, so at this point in the hyperterminal, it's actually downloading another bit stream to a peripheral FPGA, and it says hi. Okay, that's it. All right. So now it's ready to be connected to, and now I'm in a normal Unix terminal on a PC. And I'm pinging the B2 board, and it's responding. And I'm going to run a whole bunch of different processes, but I'll just tell you which ones are important. And over on the left side here, this is the console. This is actually a command line console that we've written, and it provides you with a sort of user-end simulation interface. If you ever use Simics, it's kind of like in the same vein, where you can use this to connect to the B board. You can connect it to Simics. You can dump out state or statistics, things like that. And this yellow screen right here is actually the simulated console. So the simulated console of Solaris running in our target configuration. And as I said, all the I/O stuff is on the PC, so here it is. And what it's doing now is it's loading up the workload. And what I've done is I've loaded up a Simics checkpoint, and I'm initializing 16 CPUs on the FPGA. So I've already done that. And the next thing to do is to actually initialize the main memory of the B2. Actually, let it go. But in the background right now, we're actually streaming a 3 GB memory image over to the B2. And this process actually takes quite a while to do. This is not optimized, so we can probably initialize from compact flash on the chip. So I'm going to fast forward this part. Okay, good. So now we're done actually initializing the FPGA. And we're ready to run. We're going over a really unoptimized Ethernet library that some intern at Xilinx wrote, and it's blocking. So every round trip packet is actually serialized. So it can go much faster than that, but we just never got around to fixing that yet. So now what I've done is actually told the FPGA to run 1 billion instructions. And this is actually Simics and showing you the device activity. You can see that these are interrupts coming from a SCSI controller to different CPUs. And you can just sort of see progress going on. What you can also look at is in the hyperterminal, these are database transactions that are completing on the FPGA. And so this will probably run for about 30 seconds.
Like a TCP error in there.
Yeah, those are some benign messages. Yeah.
The TCP.
Oh, okay. So actually, what we did is we marked special instructions in the benchmark, which are purposely not implemented in our core implementation. And then what it does is it micro-transplants to the PowerPC, and then the PowerPC prints that out, actually. The Solaris console also will output something. It says bad item, but that's actually normal in Oracle. So before it wasn't showing anything, but occasionally a transaction might abort, and then it'll print out a debug message like bad item right there. So at this point, let me just pause the whole thing. And so over up there, you can see sort of the number of cycles that it took to execute 1 billion instructions. And also over there, you can on the bottom of that, you can see privileged number of instructions. And this is actually right what we expect, that in a commercial database application like this, you're roughly spending about 40% of your time in privileged mode execution. This is very consistent with everything that we've heard and done ourselves. So this is sort of a nice sanity check. And you can sort of look at the instruction breakdown, meaning that, okay, it shouldn't be called instruction breakdown, but this is how much progress each of the threads are making relative to each other. And so they're all roughly paced at the right rate. And the IPC, of course, is very low. As I mentioned, the serializing flushes. If you actually run the multi-program spec benchmarks, they go twice as fast. And you can also see the rate at which we micro-transplant. So this is how often we rely on the embedded core to implement an instruction for us. Some of the other stats I won't explain. But you can sort of see that this percentage is the miss rate of a specific, so the miss rate of a fetch per instruction. So when you add that up, roughly about a little bit over 10% of instructions are missing in the cache in some form. And you can see also the number of interrupts received, devices, interprocessor cross calls. You can see the I/O rate, which is very, very low, on the order of a little bit under once in 100,000. And of course the flushes are very high, and we're hoping to fix this problem soon. But I won't go into detail now. So that concludes the demo. And so as I talked about in the beginning, simply adopting a build-all emulation approach where you just simply realize the hardware that you want on the FPGA. It's going to be too complex. It's not tractable. So I talked about two techniques for virtualizing FPGA-based emulation, one of which was the hybrid, and the other one which is the virtualized multiprocessor. I showed you a proof of concept. We've done some early evaluation work, and things look very promising. So that concludes my talk. Any questions?
Well, there's similar projects like this. I mean, this idea of doing some hybrid emulation.
Yeah, that's a good question. UT Austin is probably the most close, and they're actually kind of working with us. But Professor Derek Chu is leading the UT FAST group at Austin, and they're looking at hybrid simulation of cycle-accurate simulation. So they want to do microarchitecture research on the FPGA, and what they're trying to do is, rather than actually building like an out-of-order core on the FPGA, you only implement the minimum amount of control logic. There's no data path to get the timing right. And so what they rely upon actually is they actually rely on something like what we have, which is a very fast functional model that can drive this detailed cycle-accurate simulation. And they actually have a paper out in Micro this year. So, yeah.
How will the B3 board change? How will the B3 board change your life?
Oh, it's going to help us a lot. I think the main problem, of course, is resources. We're dealing with a part that's probably 5 years old, and so having the B3, they're going to use the latest and greatest Virtex-5 chips, and so they have a whole lot more resources. Rather than having 4 input lookup tables, they have 6 input lookup tables, and my early synthesis results show that actually there's a pretty nice reduction in area usage. I think one thing that I'm hoping that the B3 will have is available off-chip SRAM, which is something that B2 doesn't have. And potentially I could use that as a fast way to page contacts in and out, so I can increase the number of contacts. Also, I forgot to mention, going to 6 input LUTs, you also get a nice free boost in performance. So because your logic is a little bit taller now, your delay goes down by a little bit, and you can probably run this another 25 to 30% faster in clock frequency. Yeah, I think the B3 is definitely we're actually hoping it comes out soon, so then we can actually port all this stuff over to it.
So how much of the HDL did you all write? Was it VHDL or Verilog? Or?
It was in the BlueSpec, as I mentioned earlier. And I think that's roughly around tens of thousands of lines, and then it generates Verilog. Yeah.
How many people did you have working on that for how long?
Just me for 12 months.
Did you like BlueSpec?
I do. This is not the first project I did with BlueSpec. I actually did a cache coherence protocol engine a couple years, like 2 years ago in BlueSpec. But I think I sort of have the handle on it. Yeah.
What parts of the overall system did you write in that?
So the memory controllers we didn't write ourselves. Folks at UC Berkeley supplied us with that. But all the interlink stuff, communicating across, we wrote our own implementation for that. Everything on here we wrote ourselves.
We meaning you. We meaning you.
We, yeah.
And I assume like the instruction pipeline and all the TLBs and stuff that you were talking about too.
Yeah, I implemented all of those. Yeah. So actually, yeah, I mean, I think that's the. If I went with a more traditional HTL like Verilog, I think it would have been it would have taken substantially longer. BlueSpec has a number of nice features. Specifically, the way it can model a hardware system, you can actually do things like assertions in a very special way that makes it very easy to catch bugs. Verilog also has assertions, but BlueSpec has a sort of a model that makes it very nice. But yeah.
Did Do you have any integration problems between BlueSpec and the Xilinx tools?
No, because the BlueSpec can generate, the compiler will generate synthesizable Verilog, and it's a very well-defined interface between BlueSpec and Verilog. And yeah, that protocol is actually very, very easy to do. And so to glue ourselves into, so as I mentioned, there was a PowerPC core, and it also has a bus that your stuff can connect to. All of that stuff, interfacing to that was pretty trivial with BlueSpec. And I think the synthesis results were fine. But that's also on the part of the person who designed it, because you could write very elaborate BlueSpec and generate who knows what. It's as with any hardware description language. If you can get carried away and do something really bad. Yeah.
Where does the come from?
You mean who writes the compiler?
Yeah.
Oh, it's a company called BlueSpec. Yeah. This came out of Arvind and my advisor's thesis. Yeah. So this was like many years ago, and then that spun off. I think they were working on it at Sandburst, and then it spun off into a separate company.
Have you tried any of the other System C implementations?
I have not. I have not.
Have you looked at coupling this to an execution-driven performance simulator?
Yeah, I mean, I think we're not. So you mean something that's very cycle accurate?
That's very cycle accurate, where you can feed your functional simulation or couple it with the performance
Actually, so
timing model.
this is sort of something that folks at Austin and us have been toying around with, the idea that maybe we could take their infrastructure and we can glue ourselves to them, and we can provide them in fact, for them, I think the fundamental bottleneck for their stuff is actually the functional side. At least that's what they report, although I haven't had any hands-on stuff work with what they're doing. But
for a single processor.
for single processor, I think there are still some problems when you talk about multiprocessor. If you need to get the consistency right, things like that. But for single processor, it's certainly I think low-hanging fruit to do that.
So how do you address those types of issues here? How do you maintain the proper consistency?
We have a very in-order memory system. So it's a sequentially consistent memory model. So it actually is the same one that Symix has. Because Symix is just models of flat memory, and so it is sequentially consistent.
So I guess what I'm trying to understand is, since you're virtualizing processors, you're doing some time interleaving of concurrent execution.
That's correct.
So what I understood from your slides is that's just a simple round robin.
That's correct.
A issues, B issues, C issues.
That's right. But threads can get out of order, but yeah.
If one blocks. or
Yeah,
something
one
like
blocks,
that.
exactly.
Yeah. So how do you think it's significant? I guess maybe I'm thinking more down performance simulation lines, and you're not targeting that. But how would this technique extend to a performance simulation? I mean, it seems like you're going to hit a lot of problems figuring out how to coordinate this virtual activity. It's like you almost have to lay another time mechanism on top of it.
So going back to what I talked about, the work at Austin, they actually have a timing model on the FPGA that can accept an in-order trace and then generate accurate timing for you. Now, there are a few hooks that they need to get this to work. First off, what they need is a way for the functional model to roll back occasionally. And the reason why is because to model things like branch misprediction accurately, they have to force the functional model to go down the wrong path. And so there are a couple of things that are needed that we don't have yet. But the answer is that they've worked out a solution that can take an in-order trace in general and then get you the accurate timing. And they do this by virtualizing actually the clocks. So they can have a virtual target cycle, and it's completely decoupled from the underlying host cycle. Yeah.
I'm a little familiar with that, and I understand, I think, how they do it in a single-threaded model. But
Right.
you start going to concurrent execution, it seems like that's going to be difficult.
I agree. And I don't think I have a concrete example or a concrete solution for that. And I've actually mentioned this to Derek. This is quite a challenging problem when you go to concurrent execution. How do you get the right memory order interleaving? That's the issue, right? The memory order interleaving has to be it's affected by the timing, right? And a functional model like ours doesn't capture that accurately. That's correct.
Is anybody going to be using your stuff?
Within our lab, of course, there's always a lag between when you actually get the prototype and the paper out and when you have it production ready and graduate student proof. So, I mean, we're looking at probably by the end of the year, our own lab can actually start using this in the various research projects at CMU. So I think it's coming along pretty nicely. I think the 16 CPU works well just because so much of the research that's been done uses a 16 CPU configuration. So people will be able to use this to generate very fast checkpoints.
Well, thank you.
All right, thanks.